So let's start off by talking about sp orbitals. Sp orbitals form, or can be considered to form, when we mix an s and a p orbital. Now you may be wondering, why on earth would you want to do this, or what does this have anything to do with? Well, two types of molecules we might look at might be something like beryllium difluoride. Now beryllium is not really a metal, so we can imagine these bonds being covalent, shared electron pair, lone pairs on fluorine. Beryllium only has 2 valence electrons, so it pairs up with an electron from fluorine with this Lewis structure here. Now, from valence bond theory, bonds form by the overlapping of orbitals. So when we think of overlapping of orbitals, usually we want to think of one orbital from beryllium overlapping with one orbital from fluorine, then a different orbital from beryllium overlapping with the other orbital of fluorine. So you might be picturing a 2p orbital for fluorine. Now, how are we going to get overlap when we start thinking about beryllium being in the second row of the periodic table? So it has access to like the 2ps, 2px, y, and z orbitals. And the 2px, y, and z orbitals might be these orbitals here, sticking straight up and down. Those don't seem to be very good orbitals to use for overlapping, but what if we take the 2s and then one of the p orbitals that's on the axis of the beryllium atom, and then mix those together in such a way that we get one orbital pointing one way and then a second orbital pointing the different way. So this would be orbital 1, orbital 2 by the mixing of an s and a p orbital. Now this isn't geometry per se, this is just recognizing that we're going to take 2 orbitals from beryllium, one of the most stable, the s, and then one of the p's, mix them together and get 2 different atomic orbitals, or what we'd call hybrid orbitals on beryllium, so that we can get overlap. So we get hybrid orbital 1, overlap, hybrid orbital 2, overlap. So what we're doing is trying to construct orbitals on our central atom to have overlap with the atoms that we know to be attached to these atoms within these types of structures. So then another type of molecule that fits into this type of bonding is something like CO2. So you have C double bond O. So we can picture oxygen atoms kind of having perhaps an orbital here. Now, how are we going to get an orbital on carbon? Well, what if we have 2 sp orbitals? So we take an s and a p from the carbon atom, hybridize them together, and so we get 2 sp orbitals. So orbital 1, orbital 2, so we get our overlap here. Now, unlike beryllium difluoride, we have double bonds here in this molecule. Where do the double bonds come from? Well, those are going to come from the other 2p orbitals that aren't hybridized. So we have the p, let's call this axis here the px, and then this axis here the y-axis. So the py and the px are left over from the hybridization process, so they can overlap to make the second bond, the pi bond. So the pi bond forms by the overlapping of these vertical orbitals. And so then we're going to have to use a slightly different orbital. There's some pictures of this later, but if you can start picturing this now, that we're using these unhybridized p orbitals to overlap to make a planar type bond, that's where the double bonds are coming about from. So when we look at C double bond O, we can look and start seeing that one of the lines represents a sigma bond from the overlapping of hybrid orbitals, and then one of the other orbitals is a pi bond from the overlapping of the vertical p orbitals. And then the same thing for the other orbitals. So CO2 would have 2 sigma bonds and 2 pi bonds. We're going to develop these ideas a bit more as we continue throughout this topic. So beryllium difluoride, we have sp orbital number 1, sp orbital number 2, overlapping with the 2 fluorine atoms to make the bonds between beryllium and fluorine. So beryllium would have 2 unused orbitals. It would have an unused orbital here and an unused orbital here. So these would just be unfilled orbitals that, like CO2, can use for bonding. So then if we look at something like beryllium boron trifluoride, BF3. So we have BF3, Lewis structure, no lone pairs on boron, so we know this should be a perfectly trigonal planar structure, 120-degree bond angles around. So how are we going to get overlap with boron, where the boron atom has things like p orbitals? So if we think of our central boron atom, we have an s orbital, perhaps a p orbital. How are we going to get overlap with fluorine atoms? One here, at 120 degree bond angles and one here. Well, the answer would be, well, what if we mix the s with two p orbitals? So we take the, let's define these axes to still be x and y. So let's take the 2s orbital of boron plus the 2px and the 2py, leaving behind the z-axis in the plane of the page. Let's leave that one behind. So we mix these together, get three new orbitals. So our new orbitals, our hybridized orbitals, point in the direction of our trigonal planar geometry, so we get overlap for the F atoms that are 120 degrees away from that boron atom. So then we get our overlap. So we get overlap into making something like BF3. So if we have three substituents, no lone pairs, trigonal planar geometry, then we need 1, 2, 3 hybrid orbitals, and we get there by taking 1, 2, 3 atomic orbitals on boron, mixing them together, hybridizing them within this model for sp2 bonding. So we look at boron here and recognize that the boron atom would be sp2 hybridized, and then we'd have a leftover, we'd have one more p orbital, that pz sticking straight out of the page. We'd have this orbital here, that would be one unfilled orbital. So now if we look at carbon, carbon's going to form with 4 bonds, often with a tetrahedral arrangement. So if we're picturing something like CH4, we know that we need bonding, we need orbitals pointing in the direction of a tetrahedron. So we need 1, 2, 3, 4 hybrid orbitals here, so we're going to have to hybridize the full set. We're going to take the 2s of carbon, the 2px, the 2py, and the 2pz, mix all 4 of those orbitals together, so 1, 2, 3, 4 in terms of the number of orbitals, and we get 4 hybrid orbitals. So we go hybrid orbital number 1, 2, 3, and 4 centered around the carbon atom. We then could have overlap with things like the hydrogen s orbital. So the hydrogen atom can then overlap with these orbitals. So the idea of hybrid theory is if valence bond theory says orbitals formed by the mixing or the overlapping of atomic orbitals, and we don't have like a natural atomic orbital where we need it to be to overlap with the atoms and the geometries we know them to exist around a central atom, then let's hybridize our orbitals. So linear molecules go sp hybridized, trigonal planar molecules would go sp2 hybridized for that central atom, and then tetrahedral molecules will go sp3, because we'll have 4 substituents here, 3 substituents here, 2 here. So 2 substituents, we need 2 atomic orbitals to mix together. 3 substituents, we need 3 atomic orbitals. 4 substituents, we need all 4 atomic orbitals to mix together. So what about water? Well, water, we can get our bonding from sp3 orbitals and then have 2 electron pairs within 2 of those orbitals. So sp3 hybridized in terms of the central oxygen. Hydrogens overlap with the 1s with that sp3 hybrid orbital of oxygen, and then the lone pairs then are occupying orbitals where those electrons get closer to the nuclei, repel the bond pairs together, so we get an angle slightly less than 104.5 as we would expect for water. Okay, so we get a bond angle closer to 104.5 because we're in this base structure of tetrahedral with a sp3 hybridized oxygen atom, and the lone pairs on oxygen are residing within those hybrid orbitals as well. So we can try to explain hybrid orbitals for hypervalent molecules, though we don't quite discuss these so much anymore. So when we're looking at structures like PF5, which takes that trigonal bipyramidal structure, or something like SF6, which takes the octahedral structure. So if we're talking SF6, that these structures here are taking a, have a larger hypervalency, if you will. So we have 5 constituents on phosphorus. Now, some books, and we used to talk about how that phosphorus could be said to be sp3d hybridized. We're going to take one of the 3d orbitals and mix it in. And so we're just going to get orbitals pointing in the direction of the trigonal planar structure. And then for the sulfur, then we could take a second d orbital for an sp3d2 hybridization. So that's going to give us 1 plus 3 plus 2. So that's 6 orbitals, all pointing in the direction of an octahedral structure. Only problem here is that it doesn't quite seem that there's real bonding from the d orbitals in these molecules. So you can describe perhaps that molecules that are trigonal planar or trigonal bipyramidal in nature like PF5 or sp3d hybridized, and central atoms that are octahedral in their arrangement would be sp3d2 hybridized. This works or would only even explain period 3 and below because we don't see this hybridization for second row atoms, but theoretical studies suggest that, that we really don't have this actual mixing of orbitals. So a more detailed understanding of what's going on in the bonding of these molecules would be required to understand them. So we're not going to talk quite about the type of nature involved in the atomic orbitals in hypervalent molecules like PF5 and SF6. So our hybrid orbital summary for what we need to know: if we have linear molecules, then we can describe the s and the p orbitals as mixing together to give two sp hybrid orbitals. So hybrid orbital 1 and 2. Trigonal planar molecules, 3 hybrid orbitals, take an s and 2 p's, mix them together for orbitals 1, 2, and 3. And so we'd be leaving behind, think about the leftover orbitals. I'm going to go in green for these. So we're going to leave behind this orbital here and this orbital here from the hybridization process for sp. We're going to leave together one p orbital. So we have 2 p orbitals that are unhybridized left over. We have one p orbital that's unhybridized with an sp3, and then we have 0 p orbitals left over. So we have no p orbitals left over with sp3. Now the thing that's really relevant that we'll be seeing some structures on here in a minute is these leftover p orbitals in sp and sp2 hybridization allow for multiple bonds to form. So let's take a look at some of those types of examples. So if we were to look at the difference between sigma and pi bonding, a sigma bond is kind of like a S-type bond, a bond that is symmetrical with the bond axis. So if you imagine the bond axis, our bonding in this region here is symmetrical about the bond axis. That's what we call a sigma bond. Then a pi bond is kind of like a p-type orbital bonding. It's that planar bonding from these p orbitals that are overlapping together. So you get this overlapping in this plane. So a pi bond, I like to think of this as a planar bond, and the sigma bond as a symmetrical bond. It's symmetrical about the bond axis. So planar versus bond axis symmetrical. So then when we look at molecules such as ethylene, so ethylene is C2H4. So C2H4 for thinking of a Lewis structure, double bond C, so we get 4 bonds to each of the carbons, single bonds to 2 hydrogens from each carbon, so each carbon has 4 bonds. So then we would get sp2 hybridization for trigonal planar sp2 hybridized carbon atoms. So we should expect these bond angles to be close to 120. 3 substituents, so we go sp2 hybridization for the carbons, and then we want to align the p orbitals so that they overlap together to make one of those pi-type bonds. So this double bond here ends up being a sigma bond plus a pi bond. So we get the sigma overlap of the sp2 hybrid orbitals. So we have hybrid orbital 1 and 2 overlapping here. So that's our sigma bond. So that's the sigma bond. And then the pi bond is from the overlapping of the leftover p orbitals. So that's our pi bond. So we get a sigma and a pi bond with the double. And so then if we think of acetylene, C2H2, C, C, H, H, then we want a triple bond. If we double check our count, 4 for each carbon times 2 plus 1 times 2, 10 electrons. We get 2, 4, 6, 8, 10. So triple bond is within this structure here. So then we're going to get an sp hybridization. So sp hybridization would look something like sp hybrid 1 and 2 for the one carbon, and then 1 and 2 for the other carbon. So we get hybrid overlap. Then we're going to get p orbital overlap for one pi bond, and then we get the other pi bond overlapping. So we get 2 pi bonds that are forming overlaps together. So when we see H, C, triple bond CH, that triple bond is a sigma bond plus 2 pi bonds. So we get the sigma bonding overlap for one bond, and then we get pi orbital, or the p orbitals overlapping to make pi bonds 2 times. So the whole molecule, if we want to describe the entire molecule of acetylene, we'd have a total of 1, 2, 3 sigma bonds, and then a total of 2 pi bonds. So localized versus delocalized electrons. Like a localized bond is like that in acetylene or ethylene, where ethylene having this double bond here, this is a localized bond, meaning that that double bond is located exactly between those 2 carbon atoms. Now contrast that with something like ozone, which has this structure here, so which can resonate that double bond over to here. So this double bond here is not localized between those 2 O's or these 2 O's. It's spread across the whole molecule. So remember how ozone would best be described as having this 1 1/2 bond. So ozone would be best described as having a 3/2 bond, where both bonds are the same. This is delocalization. So delocalized electrons are electrons that are spreading themselves out across more than one set of 2 atoms, or more than one particular covalent bond. So we see this example with benzene. So if you picture a molecule of benzene perhaps written this way here, where you might see 2 double bonds, hydrogens, and of course we could have written the double bonds here, here, or here, and written the structure equivalently in terms of what we're representing. Like this structure would have the same like energy, if you will. There's nothing that makes one structure different from the other than where exactly the double bonds are being made. So if you imagine carbon 1, 2, 3, 4, 5, 6, 1, 2, 3, 4, 5, 6. So in structure 1, we have a double bond between 1 and 2, but a single bond between 1 and 2 in structure 2. Now the answer is, or the issue is, that these double bonds would really not truly be localized between either 1 and 2 or 2 and 3. They're going to spread themselves out across all the bonds equally, such that each bond is a 1 1/2 bond, or a 3/2 bond order in terms of the length of the bonds all being equal the whole way around the molecule, and the bond types being exactly the same. There really being no difference between carbons 1, 2, and 3. Both those bonds between 1 and 2 and 2 and 3 are both the same, because we're going to delocalize those electrons, and you can draw like a dash like this or a circle to indicate that delocalization. So we have delocalized bonding within benzene. Anytime we have resonance occurring, that's delocalization. So we would probably be done with our discussion here if not for this problem or this issue. So you take oxygen, O2 molecules. So you have oxygen, Lewis structure that we draw to this point would look like this. And if you're thinking of everything we've talked about so far, you'd probably be saying these O's would be sp2 hybrids. You'd have 2 electrons in hybrid orbitals. They would be spin paired. Like, why wouldn't they be spin paired? So you'd imagine all these electrons here being spin paired relative to each other. Bonding electrons go into orbitals. You would usually imagine them being spin paired as well. So then you take a liquid oxygen sample, pour it between 2 magnets, and the gas sticks between the magnets. That means oxygen has a magnetism associated with it. Oxygen is actually paramagnetic. Now we learned back in chapter 6 that atoms that have an unpaired electron, or more than one unpaired electron, one or more unpaired electron, would be characterized as being paramagnetic. So the fact that oxygen can be observed to be magnetic in this sense means that the oxygen atom has to have at least one unpaired electron. Now oxygen has an even count of electrons, so it's going to have an even multiple of unpaired electrons. It turns out each O atom has 2 unpaired electrons. But why is that? When you look at the Lewis structure, there certainly doesn't appear to be any unpaired electrons. How is it that oxygen ends up with unpaired electrons? Well, this is going to lead us into a discussion of what we call molecular orbital theory, another bonding topic or another bonding model to perhaps more accurately describe what's going on in the case of bonding in diatomic molecules. We can apply molecular orbital theory to larger molecules, though we're not going to consider anything larger than a diatomic molecule in this section. So molecular orbital theory, like wave properties, are used to describe the electrons in a molecule. Molecular orbitals have characteristics like 2 electrons per orbital. Electrons in the same orbital have opposite spin. So we're applying the same rules in molecular orbitals. So if we can come up with a molecular orbital diagram for, say, hydrogen, 2 H atoms, each with an electron, compare those spins together in the H2 molecule through what we call a sigma bond. So the H1s orbital spinning around its nucleus, the other H electron spinning around its nucleus. What they're going to do is pair up in such a way that the electrons have opposite spins of each other, because electrons are going to go into molecular orbitals in the same way that they go into atomic orbitals, maximizing spin or pairing them up when they're going into the same orbital. Then we have the existence, or just kind of physics tells us, if you have an orbital go down in energy, because we know bringing 2 H atoms together drops the energy until they're brought together too close together, then the energy starts to go back up. We talked about this before. It's about 0.74 angstrom for H2 in terms of that ideal bond distance. And so for hydrogen, 2 electrons going in to the bonding orbital is the best for it. If you try to put 3 electrons into H2, then you'd be putting more electrons into an antibonding orbital, which goes up in energy. And so by however much energy you go down, the antibonding orbital at least goes up by that much energy. And so we could theoretically fill 2 electrons in here, but that would be H2 2 minus, and probably not too stable. We're not coming up with any energetic benefit to putting more electrons in this type of molecule. That's just going to lead to less stability than having only 2 electrons. So H2 with 2 electrons is the best arrangement of electrons and count of electrons for that particular molecule. So molecular orbital theory could look like this. You take the 2 H atoms. I like the picture of 1 H over here, 1 H over here, each bringing forth their 1 electron. The spin of the electrons is pretty much irrelevant until they're trying to pair up to make their bonds. So you have 1 electron, maybe it's spinning in a clockwise fashion. So you're clockwise spinning electron here, and then the other electron should be spinning counterclockwise. So counterclockwise here, and so then we might draw it downward here. So these electrons are bringing the nuclei together as we're making the bond, and so these electrons are pulling the atoms together and meeting in the center of the molecule. So our greatest probability for hydrogen of where we're going to find an electron is going to be between the 2 nuclei. So if we remember that the shading of orbitals, we're going to have the greatest probability of finding the electron in the center of the 2 nuclei, and then some lower probability further away. So we can think of probability distributions like we did for orbitals to kind of give us a sense for the shape of orbitals, of this being a bond axis symmetric bond or a sigma type bond. So it's a sigma 1s because it's made about by the 1s orbitals of hydrogen. So then we could also have a sigma 1s star orbital. This is the antibonding orbital from the 1s orbital overlap. And so if we had perhaps a theoretical molecule, H2 2 minus, try to put 2 more electrons in here, we're going to put 2 electrons in between the nuclei, then we'd be putting 2 electrons. Their probability is going to be for them to be far away from the nucleus, and so that would be where the other 2 electrons would go, so they'd be more over in this region here in the molecule, the other 2 electrons making the bond, bringing the nuclei together. So the net effect of bonding and antibonding is to cancel out making the bond in the first place. So if we have 2 bonding electrons, 2 antibonding electrons, we have no net bond. So the net bond order here would be 0. So that's not really going to form. That's not going to be a stable molecule that exists, whereas H2 has stability because we're bringing those nuclei together. The electrons are more stable if they're being brought together between the 2 H nuclei. So an energy level diagram for something like hydrogen would look like 1 electron coming in, the other one pairing their spins together. So we get 2 electrons in the 1s orbital, none in the antibonding orbital. We can calculate bond order by taking the number of electron pairs that are shared between the nuclei. And so one way of calculating that would be taking the total number of bonding electrons and then subtracting the number of antibonding electrons. So that'd be 2 minus 0. If we have 2 bonding electrons, that's 1 electron pair. That's why we got to cut this in half. So we want to get a bond order of 1 for a single bond. Bond order of 2, double bond, 3, triple bond, fractional for some fractional bond. So we did the example of H2 2 minus, and it probably can't exist. What about helium 2? Can we form a molecule between two helium atoms? Well, what we would do is start with two spin paired electrons for helium, same thing for the other helium atom, so we get a bonding orbital and an anti-bonding orbital. Now, one consequence of physics is if this drops, say, by x, the amount that we stabilize helium by, the amount of energy that the anti-bonding goes up is always a little bit greater than x. So we're going to get a little bit of instability if we try to make helium compared to helium-2 compared to having two separated helium atoms. So our bond order, 2 bonding minus 2 anti-bonding electrons, no bond can form between two helium atoms in this case here. So helium-2 would not exist as any kind of stable molecule. Now, even some molecules that have a bond order that's not 0 may not be the most stable molecule in the world. Like if you look at, say H2 minus, and say, well, let's kick one of these electrons out here. So H2 minus would have a bond order equal to 1/2, 2 bonding electrons minus 1 anti-bonding electrons for a bond order of 1/2. Now, H2 minus can exist as what we would call a stable ion, meaning you could get it to form and you could characterize the anion, but it may not necessarily make it stable enough that it's going to pair up with some metal cation and make an actual ionic compound. So it's stable enough to exist, but maybe not stable enough to exist in some sort of real compound that you could actually form and ship around the country or manufacture. So it exists in a theoretical sense. Like you get it to form, or not necessarily in a theoretical sense. It exists in a sense you could get it to form perhaps in the gas phase, you could characterize it, but it's going to be reactive and still not necessarily persist for a very long amount of time. So then let's move on to lithium. So lithium is kind of like hydrogen in a way. It has one valence electron. So if you just look at the upper part here, you get a diagram that looks kind of just like hydrogen, where you get a sigma bond and a sigma star orbital with no electrons. And then the inner 1s electrons, if you think of lithium, the 1s electrons are probably pretty close to the nucleus and the 2s are bigger. So we're going to get a bigger overlapping combination. So if we think of x here for the 2s for lithium, this x here will be smaller. The amount of bonding that we get for the 1s will actually be a lot lower than we get for the 2s. So we're usually going to ignore this bonding here because it's really not going to be all that important. Like we're not getting that much overlap between those core orbitals. We're going to mainly focus on the valence orbitals and their overlaps with each other. So for lithium, if we had the full structure and we want to calculate the bond order, we would take the bond order to be 2 bonding electrons here, 2 bonding electrons here. So 4 total bonding electrons. These are anti-bonding electrons, so minus 2. 1/2 times 2 is equal to 1. So the bond order would be 1 for a single bond. And if you then ignored these from your count, then you would still have a bond order of 1. So you'd have 2 bonding, no anti-bonding electrons, still a bond order of 1. So if we're thinking of lithium, it means lithium-2 would have a single bond between the 2 lithium atoms. Now, lithium is a solid at room temperature. What you can imagine is that 2 lithium-2s can then form lithium-4. Lithium-4 can then form lithium-8. And this kind of keeps going for these metals, and you form a base structure of lots of overlapping s orbitals in something like the structure of lithium. Now, in the case of hydrogen, why might hydrogen be different? Well, hydrogen gains a lot of stability in sharing one electron, but not that much more by sharing a second electron. Or we're going to stay with a gaseous molecule with just one H2. For H2, we're going to end up with a bulk structure for something like lithium forming a solid at room temperature. Okay, so let's think about p orbital overlap. So when we start thinking of a given atom, let's picture something like boron. So boron atom has, say, an s orbital and, say, a p orbital. These could come together and overlap in ways of like getting overlap between the s orbitals and then perhaps planar overlap between these p orbitals. If we picture maybe something like a carbon atom, maybe we can picture a carbon this way, or a p orbital that way or this way, and also a 2s. So imagine another carbon, we get p orbital this way, vertical p orbitals. What I'm trying to get us to think of is that we almost need to picture these orbitals here as all being stacked atop of each other. We're all evolving or coming about from a single particular nuclei. Okay, because the overlap in this direction leads to a sigma type bond. This type of overlap leads to a pi type bond. likewise, this overlap here as well is a pi-type bond. So for the 3 p orbitals aligning side by side in a diatomic molecules, 2 of them give a sigma-type bond. So we get a bonding orbital, bring the electrons between the nuclei, and an anti-bonding, bringing them away from the nuclei. And then we get the 2 sort of vertical orbitals overlapping for the pi-type bond, and then the pi anti-bonding orbital then breaking that bond, or countering the effect of the bond that was made between those types of orbitals. And then if you imagine the p orbital sticking straight out of the page, would also have a pi-type interaction. So we get sigma bonding and pi-type bonding for the overlapping of p orbitals as we consider the bonding within the second row atoms on the periodic table. So we started this discussion with oxygen being paramagnetic. Let's see if we can solve that issue right off the bat here by considering O2. So the way this kind of begins is we're picturing an oxygen atom, 2s2, 2p4 configuration. Now imagine you have that atom. It's just existing with electrons here around our O atom, here, here, and then let me draw red for coming straight out of the page. Okay, so we have electrons here. I don't want to figure out which ones are where. I just have 2 electrons in one of the p orbitals and 1 electron in the other 2. And so I have electrons in these types of orbitals approaching another atom that looks exactly the same. And so I'm actually going to, let me see if I can copy. What's that? Let me see if I can undo that. Okay, let me see one more time if I can just copy this easily. Oh, that's not what I wanted to do. Okay, I'll just draw it again. So imagine we have 2 oxygen atoms that are just simply approaching each other. So we have oxygen atoms that are trying to overlap their orbitals in such a way to make a bond. So we have p orbitals, and then we have that other p orbital sticking straight out of the page. Okay, so think about the overlap that we get. The 2s orbitals are going to overlap in that sigma type sense between the bond axis. So the oxygens are coming together, their nuclei are coming together. The s orbitals have sigma type overlap. They're overlapping in a way that the overlap is symmetrical about the bond axis. So we get a sigma 2s orbital and a sigma star 2s orbital. So O2 has a total of 6 plus 6, 12 electrons. So I can get 2 electrons here, 2 electrons here. So I take 2 atomic orbitals and I make 2 new molecular orbitals. So my molecular orbitals are in the middle. My atomic orbitals are on the outside. I'm imagining I have one O approaching the other oxygen. So these oxygens we're trying to consider, what do their atomic orbitals look like? Then imagine those orbitals starting to overlap with each other as the atoms are approaching. So you can also think of this like you have an O here approaching the O here, and then we're trying to make this bond where we know it should form some bond because that bond strength is 495 kJs per mole of O2. So O2 should form over here. So we're making O2 in the middle. And so O2 is in the center here, and so then the p overlap here is going to be pretty strong, right? So we're going to have good overlap between the p orbitals that are on the same bond axis together. That's the sigma type 2p bond. And so then we're going to end up with the pi type bonding from the vertical orbitals and from the red orbital sticking straight out of the page. And so the 2 orbitals vertical overlap like this, and then the 2 orbitals sticking straight out of the page overlap in exactly the same way. So we end up with 2 degenerate orbitals equal in energy. We call those the pi orbitals because, again, those are the planar type bonds, just like the way they look kind of in hybrid theory. So we get planar type bonds, so pi 2p, and then we get the sigma, the pi star 2p and the sigma star 2p. So we get the bonding combination for the sigma and the anti-bonding. Then we get the bonding for the pi and the anti-bonding for the pi. So the pi bonding is not as strong, so the sigma, so the pi star is not as high in energy. The sigma bonding is stronger, so we get a higher sigma 2p, sigma star 2p anti-bonding orbital. Okay, so now let's keep filling in our electrons. So we're up to 4, so here is 6. Now we apply Hund's rule for 8, 10, I got to get up to 12, so I apply Hund's rule. There are the unpaired electrons. So in the molecular orbital diagram, I end up with 2 electrons in an anti-bonding orbital, leading to the 2 unpaired electrons So we get 2 unpaired electrons. So within this application of molecular orbital theory, we see that oxygen O2 should be paramagnetic. Now let's think about the bond order, because O2, our Lewis structure, looked like this. Does it really have a double bond? Well, let's count up our bonding. So our bond order, we take 1/2 times the number of bonding electrons. So I'm going to use a blue pen. I'm going to circle the bonding electrons. So there's bonding there and here. So I get a total of 8 bonding electrons. Then I'll use a green pen to circle the anti-bonding electrons. So there's anti-bonding and here's anti-bonding. So I have a total of 2, 3, 4 anti-bonding electrons. And so that works out to be 1/2 times 4 for 2. So I still would predict a double bond from molecular orbital theory, just like the Lewis structure suggests. And so one of the ways I like to think of bonding here is, where's the net bond? Like the 2s star canceled each other out. I have a net sigma bond and I have a net pi bond. Okay, and so then we're canceling out the 2 electrons with anti-bonding. So bonding, anti-bonding, canceling out, that leads to what I'd read as lone pairs. So the sigma 2s star leads to a lone pair on each atom. And then likewise, a pi bond and a pi star bond leads, with 2 electrons, leads to 2 unpaired electrons. Just in such a way, and maybe I'll write them like this. Maybe we'll write the Lewis structure of O to have the 2s electrons that canceled each other out, and then the pi electrons that canceled each other out, but in such a way that we write 2 electrons still spin paired, 2 the electrons in the same direction. So we end up with 2 unpaired electrons. So I don't know if that's necessarily a great way to think of the Lewis structure, but we're still seeing a total of 2 for the bond order, so a double bond, and all the other electrons would cancel each other out and just be what we'd consider as non-bonding electrons or unpaired electrons in the Lewis structure. So perhaps what's wrong with our base Lewis structure for O2 is considering the 2 electrons to be spin paired, when maybe if we considered that we have unpaired electrons and they just don't all pair with their spins in the same direction or opposite direction, so we end up with a net set of 2 electrons with their spins paired in the same direction for a paramagnetic molecule. So let's look at our base molecular orbital diagrams. So O2, sigma 2s2, sigma star 2s2. You can almost write configurations like you could atomic orbital configurations from chapter 6. Sigma 2p2, pi 2p4, pi star 2p2 for the configuration. Bond order 2, pretty strong bond for O2. Bond length 1.21, paramagnetic. Compare that to F2. What is F2? How does it change? Well, it just puts 2 more electrons, it has 14 total electrons. We add 2 more anti-bonding electrons. So the bond order drops to 1. The bond length becomes longer because now we're comparing a double bond between the 2 O's and just a single bond between the 2 F's. So we're getting the same prediction for bond order as we do from the Lewis structures for O2 and for F. We just got a better picture of the magnetic property of O2 through the application of molecular orbital theory. Now, no unpaired electrons for F2, so our normal lone pairs make total sense for F2. So diamagnetic molecule, neon 2 should not exist because there's no bond here. So we don't get a bond strength or bond length because there's no bond that forms for neon. Now, we'll show a slide for this in class that I think will make a little bit more sense of this, but this p orbital here, the sigma 2p is actually higher than the pi 2p. Okay, so we'll see a somewhat of an explanation for why that's the case in class, but the ordering is slightly different so that we get the pi 2p more stable than this sigma 2p, but notice that the pi star and the sigma star are in the same arrangement as they were for O2 and for F2. So we just get these orbitals switching places, if you will. And so then when we look at B2, B2 has 6 electrons, so 6 electrons go sigma 2s, 2 electrons, sigma star 2s, pi 2p2, and then we actually end up with 2 unpaired electrons. And so boron would look like the s and the p approaching like we drew them earlier, so that we get this planar type bond forming, and we actually then use the other pi bond to spread the electrons out. So we actually don't end up with a net bond between the axis of boron. We end up with a net bond using those p orbitals to make pi bonds in B2. So bond order is 1. We end up with a relatively long bond in the case of boron. Boron's bigger than, say, carbon, nitrogen, oxygen, fluorine, so we end up with a long bond. So we can compare, for example, the two single bonds. B2 and F2 both have single bonds, but boron bigger than fluorine from like chapter 7 logic. So that makes the B2 bond longer than the F2 bond in terms of the length. So longer bond should lead it to be weaker. So the bond strength here is lower compared to, actually, no, it's actually stronger. So the bond strength is stronger in the case of B2 than F2, likely because it has a stronger pi bond, perhaps. Let's look at C2. So C2, dicarbon. So C2 would have a total of 8 electrons. We're adding 2 more to boron's diagram, so we end up with spin paired electrons. Still no electrons actually occupying the internuclear axis of carbon, so we end up with a bond order of 2. Double bond enthalpy pretty high. Double bonds usually stronger than single bonds, and the length decreases due to the double bond. N2 triple bond, so we have 2 more electrons going into the sigma 2p for a total of 8 bonding minus the 2 anti-bonding for a bond order of 3. Really high bond strength, really small bond. So N2 for this series is actually the smallest because it's has the triple bond. Okay, so triple bonds shorter than double, shorter than single. If you're comparing atoms in the same row as each other in the periodic table, then the triple bond will be shorter than the double bond within those atoms. So diamagnetism is the result of electrons having all their spins paired. These substances tend to weakly repel magnetic fields. So something like N2, as an example, would be weakly repelled by a magnetic field instead of being attracted into the magnetic field. So you take liquid nitrogen, pour it through a set of magnets, it's actually going to be repelled by the magnets and not stick between them. O2 is paramagnetic. B2 is as well. So we would predict these substances, if they're poured or introduced to a magnetic field, that they would be attracted into the magnetic field. So is oxygen paramagnetic or diamagnetic? If we use MO theory, gives us a better approximation, gives us the true property that it is indeed paramagnetic. Okay, so the last topic for this chapter are heteronuclear diatomic molecules. And the way these structures look is, like say we're taking NO and trying to determine the diagram for NO, what we would do is recognize oxygen's orbitals experience a greater effective charge, so they're more stable, they're closer to the nucleus. So their relative energy is dropping, and so the more electronegative atom has a more stable set of orbitals, so they're lower in energy compared to where the energy is for nitrogen and its orbitals. And then we get the same overlap we'd expect for oxygen in this case. We look at the more electronegative atom and then choose the diagram. Like for O, the sigma 2p is lower, so we put the sigma 2p lower for these atoms, then the pi star, then the sigma star. So we go sigma 2s, 2 electrons, sigma star 2s, 2 electrons. We're putting 5 plus 6 electrons in. We got an odd count of electrons to go into the molecule. And so then we end up with 4 pi 2p electrons, then 1 pi star. Bond order. Now it's kind of interesting here that the bond order would work out to be 2, 4, 6, 8 bonding electrons minus 2, 3 anti-bonding electrons for 5 halves. So if we're thinking of a Lewis structure, we would actually go with this type of a Lewis structure here, where we'd have 5 bonding electrons, and then the remaining electrons will be non-bonding. Okay, so our non-bonding electrons might look like, in the case O, N, and let's see, I think I have one more. That's 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. So that gives me 1, 2, 3, 4, 5, 6, 7, 8 for nitrogen, 1, 2, 3, 4, 5, 6, 7, 8 for oxygen. this is a this is a weird Lewis structure drawn this way, but notice each atom actually satisfies the octet rule. Now, the book does talk about how this electron being closer in energy to the nitrogen atom probably means that that lone pair electron is a little bit closer to the nitrogen than it is closer to the oxygen. So our Lewis structure for NO before looked something like this, if you recall, where this structure here was coming about by using a double bond. But with MO theory, we see we get a fractional bond order. Now, there's no notion within like a diatomic molecule Lewis structure for coming up with such a structure. You know, like when we're doing O2, N2, F2, C2, we're thinking of Lewis structures of molecules applying Lewis structure rules. There's no way to consider, or there's no process for considering like a half bond. But we see we get a fractional bond order out for NO, and that may actually be an interesting way we could consider both atoms simultaneously satisfying the octet rule, and also perhaps simultaneously having relatively zero formal charges. It all depends where we imagine the bonding. If we imagine that extra electron's halfway in the middle, 1, 2, 3, 4, 5, we have a net, I guess we end up with a net plus charge on oxygen that way. So I don't know, maybe the formal charges don't quite work out, but at least we see a satisfaction of the octet rule by trying to think of the Lewis structure that might be consistent with that type of molecular orbital diagram. But certainly we can calculate bond orders for heteronuclear diatomic molecules by taking the base structure of the molecule for the more electronegative atom and using that diagram with that atom having a slightly more stable set of orbitals. Now, the one thing, I don't have the slide here, but you do get a base set of diagrams for molecular orbital theory on exams, so we don't expect you to memorize these types of orbital diagrams. We more expect you to understand filling electrons in from the order of low energy to high energy and putting the appropriate number of electrons in, trying to figure out which of these orbitals is bonding versus anti-bonding, which is a sigma versus a pi, what does that mean, what do these orbitals perhaps look like? Like, for example, this orbital here would look like this combination here, and then perhaps this orbital up here that doesn't have any electrons would look like this orbital here. So it'll look like larger orbitals pointing away from the nuclei. So it'll look like p orbitals that are just bigger on the outer ends of the molecule. Okay, so that's all for the the second half of chapter 9. We'll be reviewing these topics in class on Tuesday. Thanks for your attention.